Maxwell equations and also about wave propagations. Learning outcomes. After completing this lecture, you should be able to be familiar with basic vector calculus involving the vector operator gradients, divergence, and curl. Be familiar with divergence theorem and Stokes theorems and the application to problem involving electromagnetic field. Be able to derive the four Maxwell equations from laws of Gauss, Ampere, and Faraday. Understand what it means by the displacement current, and be able to apply Maxwell equation to find the field in the plane, electromagnetic traveling wave. Divergence and curl of vector field. So we have covered this previously, and this is just a recap. So we introduced the del operator or gradient operator, which creates a vector field, in which case the electrostatic field for electric field, when applied to a scalar field, is produced a vector field. And the shorthand notations of del is a partial derivative with respect to x, y, and z. We can also use the gradient operator to define what it means by divergence of any vector field A. Okay, divergence will be a dot product, and then curl will be a cross product. Divergence of A will be that del operator dot with that vector field A, and that gives you a scalar field. So you basically do a partial derivative of each of the components with the respective directions, and that gives you the divergence of A, and then it produces a scalar field. And then curl. Okay, so again we use that del operator, cross products with our vector field A, and then the cross products you can use determinants, a 3x3 determinants. First row is the unit vector of each directions, and then second row will be the coefficients of the vector of the del operator, which is the partial derivative, x, y, and z. And then the third row is the coefficients of the vector field A, which is A sub x, A sub y, A sub z. Just recap, your del is and then your A okay. I hope you by now you should know that writing it this way, what I'm actually writing is AX in the x direction, AY in the y direction, AZ in the z direction. Or in maths, you write this as AX I, AY J, AZ K. And then in short, we write it this way. So your curl is the vector, unit vector on the top row. Second row is this. Third row is this. And then you just do your determinants. And then you end up with another vector. The curl of A is also another vector field, and we can solve this in each component. The x components will be, so x component will be this, x component will be this times this, which is your del AZ over del y minus this times this, which is del over del z times a y. And then similarly you can do for your y and your z by going through that determinants. Divergence theorems. So we assume this without proof. So consider some closed surface S which encloses a volume V and that some vector field A is present within this volume. We have a closed surface volume. I keep talking about a bubbles. If you blow a bubbles, there will be a closed surface that has a volume. So the divergence theorem that that's the volume integral of the divergence throughout the volume V is simply the flux A through the closed surface S that bounds the volume V. Okay, so what is that? Is the integral of the divergence A over that volume is equals to the closed surface of A over that surface. So these are mathematical statements of divergence theorems. So which means that this integral is equals to this integral. So the divergence integrated over its volume is equals to the vector field integrated over the closed surface. And that is what divergence theorem is about. We can apply that to our electric flux density D. Okay, so this is our theorem. This is our divergence theorem. We're simply replacing our vector field A with our electric flux density, and therefore we have del or divergence of the electric flux density if we integrate it over the volume V, and the electric flux density integrated over the closed surface S. And then we have our Gauss theorem or Gauss law, which is the closed surface integral of the electric flux density has to be equal to the charge enclosed inside that closed surface. We'll look at this in the earlier topics on Gauss law. And the charge distribution with some volume that has a charge density rho, and therefore we can write down that the charge enclosed will be the integral of the volume over the charge density. Okay, so if the charge distribution is not uniform inside the volume that has a charge density rho, then we can work out the total charge enclosed, which is the integral of the charge density over that volume. What it means, this is equals to integral V rho dV. So this is this, okay, so this is this, and this is this, and therefore we can substitute this into that. The integral V del dot D divergence over the volume V is equals to integral V rho dV. This and this is the same. Okay, therefore we can conclude that the divergence of D is equals to the charge density. So that is your first Maxwell equations. The divergence of the electric flux density is equals to the charge density. So this is my first Maxwell equations. And then we have this relationship, the electric flux density equals to epsilon R, epsilon naught E, and this is called a constitutive relation between the electric flux density and the electric field. Statements below in red, the first Maxwell equation together with the first constitutive relation form the basis of the whole electrostatics. So this equations is everything we have learned about electrostatics. So we have spent so much topics about electrostatics, and Maxwell sum it all up in one equation, or two actually, this and this. Second Maxwell equations, the first one is on electrostatics, second one is on magnetostatics, so our B field. Again, following the same arguments, again this is our closed loop integral of magnetic flux, and we said that there is non-existing of magnetic monopole, meaning that our magnetic flux, if I have a closed surface, you always have one going in and one coming out, because it's form a loop, because it's always come in a pair. So this means that this part of the equations will be equals to 0. So the closed surface integral of the magnetic flux, this is always equals to 0, and therefore we end up with the divergence of the magnetic flux density is equal to 0. And this is the second Maxwell equations. And then the second constitutive relations, we have the magnetic flux density equals to mu r mu naught times the electric field intensity, H. And then we have the Stokes theorems. So to derive the third and fourth Maxwell equations, we need another vector calculus theorem called the Stokes theorem. So suppose we have a surface S bound by a loop L. So we have a surface S. So this surface S will always have a closed loop that going around it. And what Stokes theorem says is that the closed loop integral of the vector field A will be equals to the surface integral of the curl of vector field A. Divergence involve your bubbles. Stokes theorems involve a plane. So you have plane has a surface, and then you have a closed loop around that plane. So this is the surface integral of the curve equals to the closed loop integral of the vector field. Again, now we're going to apply this to our electromagnetic. So our Faraday's law, which we have just learned just now, V equals to minus d phi by dt, the rate of change of the flux linkage, give you the induced voltage. Can write the flux linkage as the surface integral of the magnetic flux density. So integral over the surface B, and the potential difference developed across the ends of the circuits is simply equals to the line integral of the electric field around the loop formed by the circuits. V equals to closed loop integral E dl. So normally we write V equals to minus E dl. In this case here, we're not going to use the minus sign because the rotation sense will take care of itself from the B field. So we're just going to write V equals to E dl. So we have the voltage developed across due to the electric field, integral E dl, and this is the flux. Okay, so our surface integral B dot ds, that will be equals to our flux, and the rate of change of the flux, which is Faraday's law, will be equals to the voltage developed across the terminals. So now you're linking the electrostatics to magnetostatics to Faraday's law. Okay, here is electrostatics. We learned E dot dl integral that gives you voltage. Here from Faraday's law, we learned that d phi by dt, rate of change of flux, gives you the voltage. And therefore we can put this into the integral. You have the integral cross surface dB by dt dot ds. And then we can apply Stokes theorems. So Stokes theorems here, the closed loop integral of the electric field will be equals to the curl of the electric field over the surface. And this is equals to this bit here. Okay, again like before, this is the same, and this is the same. Therefore, we can conclude that the curl of the electric field is equals to the rate of change of the magnetic flux density, or negative the rate of change of the magnetic flux density. And this is called the third Maxwell equations, and is also known as the differential form of Faraday's law. And this links the electrostatics to magnetic field, or the magnetic flux density. That equation linking E to B is one of the greatest unifying equations of science. Before that, E and B are thought to be two independent things that have no relations to each other, and Maxwell showed that they are actually related to each other. And the other constitutive relation is your current density is equals to sigma times the electric field. So this is actually Ohm's law. Sigma is the conductivity or the electrical conductivity. So for static field, equation 6, the curl of E will be equal to 0, because if you do a closed loop integral of the E field, that will be equal to 0, and therefore there is no overall work done in moving an electrical charge around a closed loop in electrostatics. If I have a charge, if we move this charge back to the same point, we said that there is no work done. Okay, so therefore the integral of the electric field over a closed loop will be equal to 0. So that is your third Maxwell equations. Curl of E equals to minus the rate of change of the magnetic flux density. And then the fourth Maxwell equations is related to your Ampere's law. So Ampere's law, so we use H instead of B. Earlier on when we write Ampere's law, we said B dot dl equals to mu naught I. And this is a closed loop integral over a closed loop. And then the current I is a surface integral of the current density. We have a current density, so the total current is integrating over that surface where the current is flowing. And then again, applying Stokes theorem, we end up with the curl of the magnetic field intensity is equals to the current density. So that is not all to it, okay, because there is something more to that equation. The curl of the magnetic field intensity is not only just equals to the current density, as realized by Maxwell. Okay, so consider your magnetic statics. So it is correct for static field, okay, but if you have a changing current, then you have to add something known as a displacement current to it. The displacement current, JD, which is dD by dt, and therefore you end up with your Maxwell equation will be equals to J, or curl of H equals to J plus dD by dt. Okay, so in magnetostatics, the displacement current is 0, but in a time-depending field, which means a propagating field, then you have to include the displacement current. That is basically the summary of all the Maxwell equations. The first one is the divergence of electric flux density equals to the charge density. Second one, divergence of the magnetic flux density equals to 0, which means that tells you that there is no monopole in magnet. And then the curl of electric field equals to negative rate of change of the magnetic flux density, and then the curl of the magnetic field intensity is equals to J plus the rate of change of the electric flux density. And then bottom here you have the three substitutive relations between the field. So that is Maxwell equations in a very simple explanation. Okay, I will stop here for today, and then there is just a little bit more to cover. I will cover that in next Monday, which will be our last lecture on plane wave propagations. So all the topics that we talk about in the first 8 topics is all about statics, and then in plane wave propagations, this is when the field actually moving in time in the free space.